Very powerful concept we're about to address. First of all, what is a differential equation? It is an equation that is differential. It is an equation. This is the very fundamental explanation of it, but this is an equation that involves slope or a derivative, often shown in the Leibniz notation, which you'll see in a minute, which is like dy over dx or ds over dt, one of those kinds of things. Okay, old stuff, you've seen it before. A direct variation is basically something that is proportional. Direct variation, and this is going to be proportional. That word's going to come up a lot. And this is basically y equals kx. It doesn't have to be y, it doesn't have to be x, it doesn't have to be k, but we do use k a lot. And this is multiplication, lots of parentheses here, proportional multiplication by a constant. It's a constant of proportionality. It's basically, it's a line essentially, but it is a line that goes through the origin because it's like plus 0. Inverse variation is y equals k over x, and this one's fairly obvious. This is division, which I'm not spelling correctly. Let's try that again. Division by a constant. Man, spelling, constant. My hand got ahead of my brain. Or I just misspelled it. Constant. I don't have a word for this one like I had for that one for proportional. All right, let's read carefully. The process with these is really just one of reading very carefully. Newton's law of cooling, okay, states that the rate of change of the temperature, rate of change is important. Oh my goodness, I might just underline it in green just because I feel like it. The rate of change of the temperature of an object is proportional to the difference between the temperature of that object and the ambient temperature. Whoa, what? Ambient temperature? That would be like room temperature. Okay. Write the differential equation that represents the rate of change of the temperature of your soup, S, T minutes, that is not S of T, that is the temperature of your soup, which is S, T minutes after you placed it into your refrigerator, which is set to 38 degrees Fahrenheit. Okay, feeling overwhelmed? Do not panic. Write the differential equation that represents the rate of change of the temperature. Okay, we need an equation that says okay? D what? D what? D S dt. And they told us what all this stuff represents. So S is the temperature of the soup, and you might say, why don't they use T for temperature? Because T is time, which is minutes. Okay, so the rate of change of the temperature of my soup as time changes is, and let's just keep reading, right? The differential equation represents the rate of placed in the refrigerator, which is at 38 degrees Fahrenheit. Okay, that's the ambient temperature. This little guy right here, switching colors a lot. This is the ambient temperature. Sometimes we call it the room temperature, but this is in a refrigerator, so it's not the room. Ambient temperature, there we go, temperature. So let's go back and read the first sentence again. The rate of change of the temperature of an object, with respect to time, is proportional to direct variation. The difference I'm about to subtract what? The temperature of that object. What's the object? It's soup, represented with an S. The difference between the temperature of that object and the ambient temperature, which is 38 in this case. That's it. That is a differential equation. That's all there is to it. We just have to read carefully. Let me read it one more time. The rate of change of the temperature is proportional to the difference between the temperature of the soup and the temperature of the refrigerator. So the rate at which this temperature changes is modeled by this equation. Let's slide up. The position of an object moving along the x-axis is given by x of t, where t is measured in seconds. X is a function now. Fun. For the first 60 seconds of motion, the acceleration, that is the second derivative, The acceleration of the object is inversely proportional to the square root of time. Write the equation that models this situation. Okay, let's proceed. Read it again carefully. The position of an object is given by this. For the first 60 seconds, the acceleration of the object, the acceleration is the second derivative, okay, of what? Displacement. In this case, x represents location. X is the location on the x-axis. You don't have to write all this every time, but it's just good to know. Where t is number of seconds. And this only applies from 0 to 60. We'll deal with the number 60 in a minute. Don't think the number 60 has to pop up in here, okay? It technically doesn't. But let's read again. The acceleration, that's acceleration, second derivative of displacement, is inversely proportional. Oh, okay, so k over something to the square root of time. Done. However, I'm going to just go a little further and say that this only applies for t values between 0 and 60. Okay, a hot air balloon is being inflated, and the volume of air in the balloon is given by a differentiable function v, where v of t is measured in cubic yards and t is measured in minutes. I'm going to write it just because it kind of helps. So v of t, I'm going to call it just v, is the number of cubic yards, and t is time measured in minutes. The volume increases with respect to time at a rate that is directly proportional to the products of time and volume. Probably should say the product of time and volume. I'm going to make that correction. It will be corrected in future versions of this. In the meantime, it's not a huge error. All right, so I'm going to just pause and write this sentence as an equation, as a differential equation, an equation that is slope. Now, you're probably like, oh, we're dealing with derivatives. We've been dealing with derivatives for a long time. Aren't these all differential equations? Yes. Yes. But now things get a little more applicable, practical, and now that we know how to take a derivative and work backwards with an antiderivative of an integral, these get much more applicable. So, second sentence again. The volume increases with respect to time at a rate. So dv dt is directly proportional to, here they come down the hall with the big floor buffer. Makes a big loud noise. About to pass by the door. There it goes. You hear it? Makes me want to adjust my lamp. There, we'll fix the lighting here. All right. Other door, I heard him. Directly proportional to the product of time and volume. So that's it. The rate of change of volume with respect to time is proportional to time and volume. We have read up to this sentence. Now they start giving us numbers. At 20 minutes, that's time, the volume is, that's V, 30 cubic yards and is increasing at a rate of 1.5 cubic yards per minute. This is starting to sound like a related rates problem, and it isn't, but we can do a similar strategy where we just list stuff. So at 20 minutes, T is 20 minutes. The volume is, it's 30. And is increasing, the volume is increasing at a rate of 1.5 cubic yards per minute. All the units match up, minutes, yards, cubic yards. And write the equation that models the situation. You might say, well, I already wrote it. Well, yes, but they gave you enough information to find K, so let's do it. So 1.5 equals, I don't know what K is, but I have 20 and I have 30. And that gives me 600. So 600K equals 1.5. We'll divide by 600. So K equals 1.5 divided by 600. I'm bringing my work up here. And that reduces sort of to 1 over 6. Oh, no, not 600. That would be the worst reduction of a fraction in the history of fraction reduction. 1 over 400. Okay, so final answer, now that I know K, I'm going to rewrite this and plug K in. Why didn't we do that on these? We didn't have enough information. but now they're telling us enough to where we can do it. So final answer, dv dt equals 1 over 400. We could write that as a decimal if we wanted. Chose not to. Times t times v, or vt, doesn't matter which order. Okay, last one. The rate of change of the population of Asheboro with respect to time is directly proportional to the population of Asheboro. This one's super simple, and I wanted to put it last because it's going to happen so much. I wanted us to end on a very common type of problem. You're going to see it a lot. So here goes. The rate of change of the population of Asheboro, they didn't even give us variables. So what we're going to do is just make up our own. So P will be the population of Asheboro. And they don't mention time, but the rate of change, oh, with respect to time, they do. So T is the number of time units, years, eras, eons, millennia, I don't know. So we are going to have the rate of change of the population of Asheboro, so dp dt, and it is directly proportional, also known as just proportional. Sometimes they'll say directly proportional, sometimes they'll say it's a direct variation, sometimes they'll say proportional. Okay? And it is proportional to the time. This is going to happen a lot.